All right, so this is number one on the 2018 exam. And so we are given a rate. People enter a line for an escalator at a rate modeled by the function r of t given by that. Again, they are not going to give you nice functions. They're going to give you stuff that's a mess. But just be aware that it's a rate. So it's going to be something per something else. And it says it's people per second. That's people getting in line for the escalator. This is a very crowded mall here. Must have been back in the 90s, right? As people get on the escalator, they exit the line because they're getting on the escalator at a constant rate of 0.7 person per second. You can decimal point that because it's a rate. So this is a rate in, rate out question. You are guaranteed to get this on the AP exam. R of t is the rate in line, and then this 0.7 person per second is the rate they get out of line. Rate in, rate out, people per second. There's 20 people in line at time 0. That's your initial condition. So that's what they're starting you out with. I wonder where this escalator goes. It must be somewhere really important since everyone's getting in line for it. Math word problems are funny. All right, you got to go with it. Letter A, how many people enter the line for the escalator during the interval 0 to 300? All right, easy enough. You just want to accumulate people from 0 to 300 for R of t. It said how many people get in line on the interval 0 to 300. This is the rate for getting in line. All right, so you just have to plug that in. All right, so it is math 9, 0 to 300, and then you're going to have to type this wonderful thing into the equation. And the reason we're using this instead of the 0 is because that's for 0 to 300. What this 0 means is at 300 seconds, people stop getting in line. So I don't know what happened. Maybe they closed the line, like, hey, we're closing the mall or something. You can't get in line for the escalator anymore. But at time 300 seconds, all of a sudden the rate drops to 0. No one else is getting in line. All right, but we want from 0 to 300. So we're going to type this before parentheses, fraction x over 100 to the third, and then a new parenthesis, 1 minus fraction x over 300, and then that is all to the 7th dx. Again, if I type anything too fast, I'm recording this. You can always go back and watch it again and pause it if you want a chance to type it in. We get 270 people. Now, this is one of those problems where you reuse part A in part B and then like reuse part B in part C kind of thing. So you have to understand what's going on. 270 people got in line during that time interval. That is what happened. 270 people got in line. All right, B, during the time interval 0 to 300, there are always people in line. People are getting in line and people are leaving, but the line never goes away completely. How many people are in line at time 300? All right, well, we started with 20. And we're going to add on how many people got in line and then subtract off how many people got out of line. We just found 270 people got in line. This is what we started with. Over that time interval, 0 to 300 seconds, we added 270 people. And then people leave the line at a rate of 0.7 person per second. So the amount of people that left is 0.7 times the 300 seconds. We're finding how many people are in line at times 300 seconds. And I'm sorry, that was a 3. That's looking a little blurry there. Let me fix it. So we started with 20. 270 people got in line, and we're subtracting out. They leave at a rate of 0.7 people per second, and we're doing this for 300 seconds. All right, so typing that in, we have 20 plus 270 minus 0.7 times, and so we have 80 people in line at time 300. So 80 people in line at time 300. All right, for times greater than 300, so the rate of people getting in line has stopped. No one else is getting in line, but people are still getting out of line at that 0.7 person per second rate. What is the first time that there are no people in line? So if people stop getting in line, but they keep getting out of line, eventually the line is going to get down to 0. So for times bigger than 300, when does that happen? When does the line go down to 0? Well, at times 300, you have 80 people. So at times 300, we found there's 80 people in line. We're subtracting 0.7 person per second. So I'm leaving that as T. and we want to make that equal 0. So again, at times 300, there's 80 people. No one else is getting in line. We're just going to subtract out the 0.7 person per second, set that equal to 0, and then solve this. So we're going to subtract over the 80. Negatives cancel. And I'm going to type in 80 divided by 0.7, and I got 114.285. I'm going to truncate that. You can put 0.286. I just like to take the first three. 114.286 seconds. Now, here's what I think is tricky about this question. And if you're rushing, like if I was rushing on this exam, I'm going to be honest, I would have lost this point because I would have overlooked this. That's the time since 300 seconds. We started at 300 seconds. This is how many more seconds went by for the line to be empty. So if you want the actual time from starting at the beginning until when the line is empty, you have to add on 300. So you have to add 300 seconds to that. Because again, we started at time 300. From time 300 onwards, it took 114 seconds. But if you want the total time, you have to add those together. So it's not difficult to add 300, but you have to remember to do that. And if you're rushing, then you might miss it. So just be careful. I was going to truncate that and I still wrote 0.286. Oh, well, you could put 0.285 or 0.286. That's what I get for trying to write and talk at the same time. All right, I'm going to have to fold this paper over so I can see what I'm writing a little bit better here. All right, part D says for times 0 to 300, at what time is the number of people in line a minimum? This is a candidate's test. You want an absolute minimum to the nearest whole number, so we're not going to decimal point a person. Find the number of people in line at that time. So they're asking you for the time and the number of people. That's why I always tell you to write out the whole statement. Sometimes they ask you for one or the other. This time they're asking you for both. The chart is your justification. All right, so this is like the fish problem. Remember I had time and then I had fish? We're going to have time and then people. We're going to have to write an equation for people. Your candidates are your endpoints and your critical points. So our endpoints are 0 and 300. Critical points is derivative equals 0. Well, first I need to write an equation for people. So you take what you started with. We started with 20 people in line. You add on however many got in line. So that's the accumulation from 0 to whenever of that rate in minus the people that are leaving. That's the rate out, was 0.7 people per second. So it's what you started with, the initial condition, plus how many people got in line. That's accumulating people that got in line, minus and the people that left. So 0.7 people per second. So we're going to do people prime. So it's going to be derivative equals 0 to get your critical points. Well, 20 is a constant, so that's gone. Derivative and integral cancel out, so all you have left is what's inside. So that's just r of t. And then derivative of 0.7t would just be 0.7. We're going to set that equal to 0. And I'm going to add over the 0.7. So what it is the rate in equal to the rate out. And that's the exact same thing that happened with the fish question. Remember, like fish entering the lake and fish leaving the lake as though they had any choice in the matter. So if you just intuitively want to set the rates equal, that's fine. You do still need this equation for people because that's what you're going to plug your candidates into. Initial condition plus people in minus people out. You still have to be able to do that. But if you set these rates equal, then you're going to be able to get your critical point. All right, so your calculator. We're going to go to y equals, clear out whatever you've got in there. We're going to put r of t into y1, and we're going to put 0.7 into y2. Again, if you want to have this question open in another tab so you can see the problem, again, I can't show everything on my screen. I don't have enough space, right? It was 44 x over 100 to the third, and then a new parenthesis, 1 minus x over 300 to the 7th. Again, it's not going to be pleasant. It's going to be a yucky function. They're not going to give you something nice. All right, and then here I'm going to put 0.7. Now the window, we want the window to be 0 to 300. Those were our endpoints. For your Y minimum and Y maximum, now I want to see where this equals 0.7, which is really small. I'm going to make this -2 to 2 just to kind of like bring that in. And we'll see how that looks. Again, if you don't like the window, you can always try something else. You can just kind of fiddle with it until you're happy with it. But I know I need to kind of focus on 0.7. So I made my Y's go from -2 to 2. And that's pretty good. I can see everything we need. So we're going to have 2 critical points. There's 2 intersections. You have to be able to store both of them. All right, so let's calculate the first one. Calculate, intersect, first curve, enter, second curve, enter. For guess, just move the cursor closest to the one that you want. And then enter. And that is our first critical point, 33.013. And you have to store that. So I'm going to leave, hit quit. I'm going to hit X enter to bring it back and then store it. So hit X enter, store alpha A, enter. Now we got to go back and find the other one. So I'm going to go back to the graph, calculate, intersect, first curve enter, second curve enter, guess. I'm going to bring the cursor closer to the other one. And that one is 166.574. And I need to store that as well. So I'm going to quit out of here. X enter will bring it back. And I'm going to store that one as B. So I have this one stored as A, this one stored as B. And so we're going to plug those into the people equation. Now at time 0, integral 0 to 0, you've accumulated nothing, and this would be minus 0.7 times 0. At time 0, you just have 20 people. No one got in line and no one got out of line. That's your initial condition. So at time 0, you've just got 20 people. All right, so now we're going to plug in this one right here. So 20 plus integral 0 to A. And then one more time, I'm going to have to type this awful function. This will be the last time though, because after this, we'll be able to bring it back to type it all the others. All right, so there's that function dx. So that's the initial condition plus the people that entered the line minus 0.7 times alpha A. So minus 0.7 person per second, and we're plugging in this 33.013 seconds. Phew, okay, enter. And so at that time, we have 3.803 people. So I don't know, I guess somebody has like 1 foot on the escalator and 1 foot off. All right, now we want to plug in B. All you're going to do is go back and bring this back and change all the A's to B's. So this A right here, I'm going to change to alpha B. You can just type right over top of it. And then the boundary on the inner, you have to change it. So again, you don't have to type the whole thing all over again. You can just go back and change the A's to B's. This one gives us 158.070. All right, and then 300, we already did that one back in part B. You can go and type in the 300 if you want. But in part B, we did initial condition plus the people that got in line minus the people that got out of line at time 300, and we got 80. So that one's going to give us 80. You can do it again, but it's just going to be 80 for that. All right, and then what was the question? Was it the maximum or was it the minimum? They're asking us for here. At what time is the number of people in line a minimum? So that is this one right here. And we're going to round to the nearest whole person. All right, so the minimum is 4 people at time 3.013 seconds. I'm almost out of room there. And the justification is the chart.